In this video, I want to talk about the USART peripheral. USART is an abbreviation for Universal Synchronous Asynchronous Receiver Transmitter, or serial for short. And the serial port can operate in two different modes. It can actually be used as a full duplex asynchronous transceiver, so it can receive and transmit at any time, so it can be a receiver and a transmitter at the same time. Or it can also operate as a half-duplex synchronous port, which has a data and a clock line. And because it only has one data line, it can only be a receiver or a transmitter, depending on the register settings. So it's kind of like a sort of SPI that only has either a receive or a transmit line. But most often the USART peripheral will be used for the full duplex asynchronous mode, where you can easily talk to other microcontrollers or also easily print out data to a computer when you connect the microcontroller through a serial to USB converter. And then you can have a look at that in terminal program and actually print out debug messages, for example. That's one very popular use for the USART. So before I go more into the details of how the USART is implemented on PIC microcontrollers, let's have a look at the data frame format. So let's say we want to send the ASCII representation of Y, or the ASCII value of Y. Then in hexadecimal, that is 79. And in binary, that's 01111001. Here I've got a graph of voltage on the y-axis and time on the x-axis. And we can see that the idle level for the data lines is high, so in this case VDD. And then the frame starts with a start bit. So the line goes low for a fixed amount of time, and that fixed amount of time is actually the inverse of the baud rate. So if we have 9600 baud, then the time that each bit takes to transmit is 104 microseconds. So the start bit is always 0. The line goes low and therefore indicates that this is the start of a new frame. After that start bit has been sent, we send our 8 or 9 data bits. That depends on the settings in the peripheral. We send 8 or 9 data bits, least significant bit first. So in this case we send 1001 first, which you can see we start at this point here and then go in this direction. And then at the end we've got a stop bit at the end of the frame, and that's always a 1, and that tells the receiver that in this case this is the end of the data frame and this is the data that I sent to you.
This is the internal block diagram of the USART transmit block, and we can see that this is the TX-reg register, which is the data, so we will write data to be transmitted to this register. And as soon as a transmission begins, the TX-reg, or the contents of the TX-reg register, get transferred into the transmit shift register, which is this part right here. And the transmit shift register is connected to the TX pin output buffer, and when the baud rate generator tells the shift register to shift out a bit, then the baud rate generator will tell the transmit shift register to shift out another bit to the TX pin. And we can see that the least significant bit here is the first bit that is shifted out, and the most significant bit is the last bit that will be shifted out. And the baud rate generator actually just is a timer and a compare module dedicated to the USART peripheral that will make sure that each bit only takes, for example, at 9600 baud, 104 microseconds. Now on the receive part of the USART, it's basically the same thing, just backwards. So we've got our RX input pin, and that goes through the input buffer. And then we've got this data recovery clock. So the baud rate generator, as soon as the data line goes low, because we've seen the start bit is the first bit as transmitted. So after the line has gone low, the baud rate generator is started. And it will tell this data recovery circuit to read the pin, the input pin value, the state, if it's either 0 or 1, and at the needed time. So at every 104 microseconds at mid-bit time, basically in the middle of the time where a bit would be valid. And then if a bit is detected, that is shifted into the receive shift register. And after the receive operation has finished, the data received by the USART gets shifted or gets transferred into the RC reg register, which we then can read to get the data we've received from the USART. And at the same time, when the RSR transfers the data to the RC reg, the RCIF, the receive interrupt flag, is set, and then we can use an interrupt, or we can fire an interrupt every time we receive a character, and that's very useful because most of the time we don't want our PIC to just pull this receive interrupt flag bit and just waste all the time just waiting for another character to be sent, but rather we want the CPU doing other things and then just getting interrupted as soon as we get a new character. Let's have a look at the source code that I will use to demonstrate the USART peripheral. So right here we've got all the configuration bits again for the PIC 16F1509, the PIC we're using, and I've configured it so that we're using the internal oscillator. And I've set the internal oscillator to 4 megahertz through the IRCF bits of the OSCON register. And you can have a look at my other video on oscillator options if you need more explanation on what oscillator options are actually available for PIC microcontrollers. And then you can see I'm calling a function called USART initialize, or init, and that's defined right here. And what we're doing is in the TX STA register, which is the TX status register, we first enable the transmitter, and then we enable, or we set the baud rate generator to a high baud rate. So we say we want to generate a high baud rate, and we have to do that because the 9600 baud communication stream that we want to, or the 9600 bauds of communication speed that we want to reach, is a little hard to reach if you're using a 4 megahertz internal oscillator clock. And we can see that from the data sheet here. If we have the baud rate generator bit not set, and in 8-bit asynchronous mode, we would divide the oscillator clock by 64 and multiply that, or we divide it by 64 multiplied by the compare value for the baud rate generator. And it turns out that if we rearrange that formula to get n, in this case, which is the value of the baud rate register, or the compare value of the baud rate generator, then we would get a very small compare value for an oscillator frequency of 4 megahertz and a baud rate of 9600 baud. So what happens if that value gets too small? The allowed error of the baud rate gets too high, and we might actually lose data, or our data stream has not the right timing. So we're using so we're setting a BRGH bit, and what that basically does is we only divide the oscillator clock by 16 now. So we get a much higher compare value, or a bigger compare value, and therefore our error will be much less, so that we actually can send out data at 9600 baud using an oscillator frequency of 4 megahertz. So that's why I'm setting the BRGH bit right here. Then in the receive status register, we enable continuous receiving because we want to continuously, or be able to continuously receive characters. And then we have to configure the I/O pins. Now on PIC microcontrollers, it's a little bit strange. We actually have to set both pins to an input in order to connect them to the USART peripheral. So that makes sense on the RX pin because that's an input, right? So first we enable the digital input buffer of the RX pin because actually the RX pin is shared with the analog to digital converter, so we have to enable the digital input buffer, otherwise the receive won't work. We wouldn't be able to receive digital values, or read digital values rather, from the RX pin. Then we set the RX pin to an input, and then we set the TX pin to an input. And now that is automatically configured to be an output once we enable the USART. Then into our baud rate compare register, or into our baud rate register, we load the value of 25, and we got that value, as I've shown before. We divided 4 megahertz by 16 times the baud rate, and then we subtracted 1 from that, and that's 25. So we get a baud rate of 9600 baud. Then on this part here, we enable the receive interrupt because we want to, as I've explained before at the block diagram, we don't want the CPU to wait for every new character. We just want the character or the USART to interrupt the CPU every time a new character has been received. And last but not least, we enable the serial port. Then we just use a function called USART put s, or put string, to send the string in it complete. And this \n right here, that's just a new line character, so that we get a line break in our serial terminal. And the USART puts register, well, it basically just takes a pointer. In this case, this will be converted to actually the address, or a pointer to the first element of this string here, which is I in this case. And it will just iterate through that string until it reaches basically the end of the string, and we'll call another function called USART put c put character, and we'll print character by, or go through the string character by character and print the string character by character, because as you've seen, we can only send 8 bits at a time. And the put character function, actually what it does is, before we write the character to the TX reg, we actually have to wait until the last transmission has been completed. So we have to wait until the transmit shift register is empty, until we can load new data into that register. So that's what we're doing. We're polling the TRMT, which is the transmit register empty bit, and when as soon as this bit gets set, then we can, that means that the register is empty, the shift register is empty, and we can actually write a new character to the transmit register. And at the end of the initialization sequence here, we enable the peripheral interrupts, and we set the general interrupt or global interrupt enable bit. And I've covered this before in the interrupts video. And down here, we've got an interrupt service routine. And what we do in that interrupt service routine, we first check if the RCIF bit, the receive interrupt flag bit, is set, because we have enabled the receive interrupt here. So in the interrupt, we have to check if that bit has actually been set. After that, we store the value of the receive register into a temporary buffer called T in this case. I've defined all these variables up here. So we've got an unsigned character T, which is basically our data buffer, our single character buffer. Then we've got the index variable for our string, and then we've got another array, which basically holds our string, because remember, in C, a string actually is just an array of characters. So it's an array of bytes. and I've defined them all as volatile because they will be used in an interrupt service routine, and they might update suddenly without the main program here noticing. In our case, that's not too critical because we're not doing anything in the main loop, but you should always define variables that you'll use in an interrupt service routine as volatile. So after we've read the receive register, we actually go into this if-else statement here, and what we do is we check if the transmit, or if the receive character is not equal to the new line character, because we want to end the receiving of a string at the new line character. So the problem with only checking, for example, in this case, we're just saying, well, as long as the receive index is smaller than the string length, which in our case is 12 characters, then what happens is if we only receive 5 characters, for example, then the string will not be finished because there will be so after we've read the RC register, we actually go into this if-else statement, and what we do is first we check if the new line character or the receive character is not the new line character. So after we have confirmed that the interrupt has fired, we read the RC reg into our temporary buffer, and then we check the temporary buffer if it's not equal to the new line character, because we want to end reception of a new string, or we want to end our string if we've received a new line character. And then at the same time, we have to make sure that our index is not, our string index is smaller than the absolute or the maximum string length, because we don't want to write to unknown memory locations, because that will cause all sorts of problems. So if we have confirmed that the RC index is smaller than the string length, and that the received character is not a new line, we actually put our character here into our string variable, or into our string array rather, at the location of where the RC index points, or at that array index, and then we increase the index by 1. And if that is not true, if we've either received a new line character, or we actually have received the maximum, or we have hit the maximum length of the string, then we will reset the string index, and we will print out the received string. So this is basically just a simple serial echo kind of program. So we send it, for example, hello, and then we'll echo back hello. So I'll load that onto the microcontroller, and then we can have a look at what that looks like. So I've opened the serial port. I'm actually using an Arduino as the serial to USB converter, because that's the easiest way I found to connect the PIC microcontroller, or to read the serial data in from the PIC micro into my laptop here. So if I hit the reset button on the PIC micro, or on the controller board, then we can actually see that we receive the init complete message right here. So we have confirmed that this works because we've set our serial terminal to 9600 baud, so we know that our baud rate is correct, and we are also using 8 data bits and 1 stop bit. And then we can also send stuff to the microcontroller, and if we hit enter, or when we hit enter, the terminal program will actually append a new line character. So if we just type hello, then we'll actually echo back hello. We could also do something like tuna. Well, and that's that's rather interesting. What you can see is actually it did not replace, or it sent tuna, and then it also sent O and a and the exclamation mark. And that is because after we have received a new string, we can look at that right here. After we've received the string, we're not clearing the string, so we're just sending that out. But because, well, what happens is the data that we received remains in inside this variable rcbuff. So, and we reset the RC index. And if we have previously sent a, for example, 6-character sequence here, then 6 characters of those 12 will be used up or will be filled with data. And then we reset the index to 0, so we'll start here and write in the new sequence that we've received, in this case tuna. So we will overwrite H with T, E with U, L with N, and L with A, but because we have not overwritten O and the exclamation mark, it actually sends that back to us. So now instead, if we send another 6-string sequence like world exclamation mark, then we will actually get only the world with the exclamation mark because we've overwritten all of the buffer here. So I hope this was useful as an introduction to the USART module. It actually is, as I said, pretty easy to use. You might have seen that from this because you don't need a lot of configuration, and it's an easy way to make your microcontroller speak to you, or you can send data to the microcontroller or get debug information out of your microcontroller. That's what I use it most often for. I will use a USART module to print out the state of a variable or something, just to make sure that my program is actually executing correctly, or that the variable increases or something like that. So thanks for watching. If you like this video, give it a thumbs up and subscribe to my channel.